If I gave you two sets, set A and set B, how would you go about combining these two sets into a new set? I'll call this set C. You might first start with multiplying each pair of terms. If you think of these sets as two functions, you can combine these functions to get a new function, which goes as follows. But there's another type of combining function, and it's called a convolution. Convolutions are not just useful for combining two functions, but they share an important role in image processing. If we start with two different arrays, I'll call these arrays array A and array B, and we'll fill them with numbers from say 1 up to 7. And our goal here is to pick two random numbers from these two arrays and find out the probability of finding various sums. To do this, we will just need to create a basic addition table. Filling in the values, do you notice anything? Well, the probability of finding various sums is just shown on these diagonals. For example, finding the probability of a 10 is just the number of 10s on this diagonal, which in this case, it's equal to 5. Then we need to just divide it by the total number of combinations, which gives us 36. But there's another way of representing the probability of different sums. For example, let's see we have our two lists, this A and this B. We flip one of the lists. In this case, I'll flip list B so that each pair adds up to 8. I'll then shift B so the end item of B is aligned with the first item of A. If you want to find the probability of the sum being 2, the probability is just the ones that align. In this case, it's just 1 over 36. For it to be 3, it's just these ones over here. Each time I'm shifting over, going down by each diagonal each time. I can do it a third time, and so on. Each item in each array has an equal chance of occurring, but we can name these chances B1, B2, B3, and so on, and A1, A2, A3, and so on, which represents the probability of, say, 7 occurring. To find the probability of a 2, we can lump this over here and multiply the two probabilities, which gives us B1 times A7. If we want to find the probability of a 3, we shift it 1 over to the right and sum the product of the terms that align. In this case, we get B1 times A6 plus B2 times A7. So how can we apply a convolution to two sets? Let's say we want to take the convolution of set 347 and 592. First thing we need to do is slump this all the way over to the left. Then we need to take the sum of the product of the aligned terms, which gives us 3 times 2, which is 6, which is the first term in our answer. The next thing we do is we shift the array 1 over to the right and take the sum of the product of the aligned terms, which gives us 3 times 9 plus 4 times 2, which gives us 35. And we keep doing this until we finish our set or the answer. And we get our final set as 6, 35, 65, 83, and 35. And this is indeed the convolution of 347 and 592. Now notice how the answer set is 5 elements, and the input set is only 3 elements. But you can apply convolutions to images too, to transform them into other images. Instead of taking a convolution with a 1D set, we take a convolution with a 2D, almost like matrix, which we call a kernel. As an example, let's apply this kernel to this image. This results in an image like this, which is called a Gaussian blur. As a simple example, let's apply a kernel to this Pac-Man drawing I made. We put our kernel So the center is at the edge of the image, or the top corner of the image. And you'll see why later. And I'll also put our resulting image to the right. Now let's start. We first look at the terms that are aligned and take the sum of the product of the colors underneath, which we store in vectors, a 3D vector of the RGB values of that color. This results in just black again. We can do this again by shifting the kernel 1 over to the right and taking the sum of the terms that align. In this case, we get black again. If you do it again, we get black again. If you do it again, we get a very, very dim yellow color. This is because all the aligned terms kind of bleeds in to the sum. This is how the Gaussian blurs actually work. If you do this for the entire image, you get an image that looks something like this. As you can see, when blurring it with the kernel, all its neighbors kind of bleed in. And to change the intensity of the Gaussian blur, you can choose a bigger kernel. In this case, we use a 3x3 kernel, which is probably most common in computers to these days. But you can increase the intensity of the blur by, say, a 5x5 kernel.